Welcome to another episode of the TechnoWizards podcast. For those of you who don't know, we are the TechnoWizards Team 16458, an FTC team in San Antonio, Texas. My name is Vincent,
And I'm Aditya.
and today we are joined by I.C.E Robotics Team 11329 from Bloomington, Indiana. They are three times winners at the Indiana Southern League Championship and were fourth place in the global OPR this year. So, first question to get to know y'all. So, first off, can y'all introduce your team and why you joined the robotics team?
Yeah, absolutely. So I suppose I'll start us off. I'm Diana Lynch. I am the lead designer and lead systems engineer for FTC 11329 I.C.E Robotics. And I really got into robotics because I've always been interested in engineering, and this program has really given me a place to express my passion.
I'm Sean. I'm the lead programmer on 11329 I.C.E Robotics. I first joined robotics because I really wanted to learn more on how to do the engineering design process and how programming could fit in with that. And it's been one of the first projects I've been able to really get into and work with the team on designing a robot.
So starting off with some mechanical questions. So what is your mechanical design process like?
Yeah, sure. So our overall engineering design process follows what you might expect. So first, we identify what our overall game strategy is going to be, create a list of features and design criteria that we must fulfill, brainstorm, make first prototypes, test the viability of design, and then keep iterating on those designs in order to gradually improve them. Our overall design philosophy revolves around simplicity and versatility. So every year we strive to make the robot extremely simple, yet still accomplish as many goals as possible. So this year we wanted to build a really small robot, somewhere around 12 to 13 inches, so that we could quickly move around the field and it would be really easy to maneuver. We had a couple design criteria, which was a fast omnidirectional drive and be able to intake and score cones through both the front and back of the robot. We specifically chose this design criteria because we didn't have it last year, and it really hurt us in auto not being able to pick up on one side and score on the opposite side. We also had a couple other criteria, such as a really low center of gravity.
So what kind of materials did you use when building the robot?
So
And what were the benefits of
all
it?
of our chassis and our structural elements are made out of aluminum. We use off-the-shelf parts from GoBuilda in order to make the introductory design a lot faster, so we can get something driving as quick as we possibly can. From there, most of our systems are either 3D printed or CNC cut out of wood. This year, we really focused on 3D printing as a tool for very quick iteration. And then the more complicated designs that we made through our CAD process, we would then get sent off to some of our local sponsors, and they would have them CNC milled for us. Most of that was out of wood, but we also incorporated some carbon fiber into our robot this year.
Okay. And why did you decide to use Mecanum drivetrain for this season?
Yeah, so a Mecanum drivetrain is, at least in our opinion, pretty much the gold standard for FTC. It's really nice because it can be really fast. You're not losing a lot of speed as opposed to something like tank drive. You can also strafe, you can turn really easily, which means you can pretty much go wherever you want without having to spend a lot of time repositioning. The main downside of Mecanum drive is obviously that it doesn't have a lot of traction. So some teams have gone with something like butterfly drive or swerve drive in order to counteract that. But the nature of most FTC games is that you're not having a lot of impact with other robots. You're not getting into a lot of pushing matches as you would maybe certain other FRC games. And so it's never really been a problem for us to just put on a Mecanum drive, which we can put together really quickly. We can get something driving really fast, and we can spend time working on mechanisms elsewhere, as opposed to something like a butterfly or swerve drive, which would take longer.
This year, we took the GoBuilda Strafer chassis and we modified it in order to be as small as we possibly could. We really strove for like a 12 by 12, 13 by 13 inch design so that we could fit diagonally between the poles on the field. So with some slight modifications, that allows us to be really quick on the field with the Mecanum drive.
Let's see. Okay. We do have a kind of funny video sharing here, which is how the robot has progressed over the season through the iteration. So the first video is at our first scrimmage. And you can see here how the initial arms and slide design is definitely there, but it's just not very fast because programmatically there wasn't a lot of time, and especially the claw is nowhere near the last iteration. And then on the right, we've got our one of our MTI matches. Let's see if we can get the left robot to place a cone. but you can see kind of how it works. And then on the right, we've got our MTI match, where it's progressed a lot, and you can see that the tuning iteration is there. And especially if you look at the claw, how the iteration process has changed it from 2 flat plates with weather stripping on it to more curved. We changed the design of the servo in order to stress it less. Okay, there we go. Okay. Diana, would you like to cover how our CAD process works?
Absolutely. So one of the things that we really strive for on our team is making sure that we're taking in physics and innovation into every step in our process. So we always like to say that it is more that we need to prove the math before we make the design, right? So that goes from torque calculations, making sure our center of gravity is low, so that our robot can move around quickly without being tippy. We use basic physics equations such as calculating torque to determine the appropriate motor and gear ratio to move our arm quickly, to constrain our servos, as well as to lift up our elevator and make sure that if one of our motors breaks, the other one is able to compensate and go past that frictive torque of the other motor to make sure that it's still working even if something is going wrong. Additionally, we made sure that the motors and electronics on the lift were mounted as low as they possibly could to keep the center of gravity low even when everything was extended upwards. We assisted this lowering of our center of gravity by including a 1/4-inch steel base plate on our robot, which placed our center of gravity very, very low and made us very fast even when we were all the way extended. Finally, one of the things that I personally love to use while I'm designing is finite element analysis and generative design, through which I assign specific stresses on the computer to different parts that I'm working with, and the computer can tell me how those work on my parts and give me more specific designs that are able to compensate for those stresses and minimize weight.
So what's the image on the right showing?
So this is one of the side plates that we used on our carriage for our elevator. This is an older version of it, but I assigned, this is pretty much the earliest version that I did before we got to what we have now. And that reduced a lot of our carriage weight and also made sure that everything was strong in case it got hit. That piece, we like to call it now the pregnant alien, based on the design that was given by the computer.
And just to reiterate, what the design on the right is showing is it's showing the FEA process. So you can see at each point the forces that are being assigned to each element, and then the computer constructs the piece as a mesh and decides which parts of the mesh need to stay to gain optimal support and which parts can be cut out. So if you want to start going through the subsystems of our robot, this is a drivetrain. As we said earlier, it's a modified Strafer chassis with a 1/4-inch steel base plate. We also later in the season added a Lexan plate on the bottom of the steel plate in order to lower the ground clearance, making it a lot harder to go over the ground junctions, because that's something we were struggling with, is the robot could sometimes get stuck on ground junctions. We ended up with a 13.5 square base, and we integrated maintenance holes throughout the entire bottom of the robot, so it's really easy to maintenance the drivetrain. So if one of the motors gets loose, like it did a couple times, it's really easy to just stick a screw in an Allen key in the robot and tighten it, as opposed to having to take off the entire base plate. We did a couple drive ratio calculations, so something like 13.2 to 1 versus 19.7 to 1 type of calculations. We originally started with I think 19.7, and then integrated to 13.2 in order to speed us up and make us faster on the field, which is something that became really important to us as the robot started to speed up.
Moving on to the arm and slide, our carriage assembly, we decided, or from early in the season, we wanted to make sure that this was incredibly versatile as well as very light. So we used a coaxial virtual 4-bar that allowed independent control of both the arm and the wrist positioning while maintaining a low center of gravity. That way we could put our servos and our motors low on the carriage while also having very precise control of everything happening at the end of our arm. This single subsystem is responsible for all the game piece movement, from picking up the cones to scoring them, which allows the movement through our robot to be a lot more simple, and we don't need a lot of complex trading off mechanisms. We designed this symmetrically to allow our robot to pick up cones on both the front and back of our robot, as well as place them there. And again, we used a lot of 3D printed parts in this system to iterate it as quickly as we possibly could. So as soon as something broke, we would go into CAD, tweak it a little bit, find out why it broke, strengthen that part, and then just print it out. And by the end of the night, we could have a brand new part, a stronger part, one that would work better for what we were trying to do. Additionally, this whole carriage assembly was meant to be as modular as possible. So if you're looking at the picture on the left, both of those white plates, those are the pieces that we were showing earlier with the finite element analysis. You can see why we call them the pregnant alien. But each of those connect with exactly 2 screws to the Go Build a Viper slides on the sides. So if we have something that breaks, all we need to do is remove 4 screws and the whole assembly comes off. That way we can quickly replace it if something is breaking. Additionally, we had some issues with belt tensioning throughout the season. As you can see, there are things that are able to move around slightly. So we used adjustable clamps that were able to keep the arm and belts in tension. Finally, like I already mentioned, the side lifts are just the Go Build a Viper slide lifts. So we could very quickly start working on the carriage assembly, the thing that would actually score for us. So we didn't have to spend more energy in places that we didn't necessarily need to, because we already have a solution that's going to work well and it's going to work fast.
So when designing this arm, did you have any like design challenges with having like a virtual foreball in your robot, and how do you solve them?
Yeah, absolutely. So when we first made this design, you can see this in some of our design progression slides earlier. We started off by mounting plates to the very top and using 2 servos on each side that would be able to drive the arm and drive the wrist. But we decided very early on that this design was going to be very suboptimal, as it placed a lot of our weight very high on our robot. From there, we switched our design to something that looked a lot more like this, where we had all of it lowered down onto the bottom of the carriage. But instead of using a motor in the center like we use now, we used 2 torque servos and a pulley that moved up to the very center. When we were designing that, we did not think about how the strength of the arm is going to make that torque servo give a lot of strain on that torque servo. So it ended up having a lot of issues with slipping, given that we used a carbon tube to constrain everything on that top shaft. So what we ended up doing is we switched those servos out for a motor that was connected by gearing chains instead of pulleys up to the top of the arm, eliminated the middle section that was allowing for a lot of slip, and made it a lot faster, a lot stronger, and a lot quicker.
So this is our claw and pull stabilizer. So the claw has gone through a lot of iterations over the course of the season. So we originally had a servo and 2 gears geared to 2 essentially plates with rubber bands on them, and that would grip cones fairly well. It went through around 9 iterations before we finally got a couple printing versions that were working. We designed an over-center linkage in order to eliminate the servo motor stress while locking onto the cone, because it means that the servo doesn't have to constantly work in order to keep grip on the cone, and we burn out servos a lot less quickly than most teams probably would. The fingers are large to allow for air when trying to pick up a cone. It means you don't have to be as precise when flying in trying to grab a cone. The pull stabilizer I think is really interesting because we integrated a beam brake in order to enable automatic cone delivery. So what that means that although you can't see it in the CAD, there are two line brake sensors on either side. And so when we push into the pole, the line is broken, and we can tell the robot to drop down and place the cone, which made us really fast when cycling. We had to integrate a servo saver, essentially a little spring mechanism on the servo on the pull stabilizer, so that it wouldn't burn itself out, because in our first couple tests, we had servos stripping themselves because there was so much torque being placed on the pull stabilizer when it would slam into the pole. The entire assembly of the pull stabilizer is held on with 2 screws and can be swapped in 2 minutes. Again, going back to the simplicity and versatility design criteria that we kind of set out in the beginning, is to keep this as simple as possible so we can take things apart and replace them extremely quickly. I've got a couple programming things that we could go over. That's the end of our subsystems design. So should I just go into it?
Yeah.
All right. So as far as programming a drivetrain, there are a couple things that we do in order to have really fluent and really quick driving. So first of all, we do a lot of driver practice and drills for various match situations. So can you place this many cones in this long? If you play against, a human acting as a robot, can you get a lot of practice? Can you win that ownership battle? But as far as actually programming the drivetrain, this year we went with a standard control scheme. So forward, backward, left, right, and then rotate on the second control stick. It's what most teams do, and it's what most docks have. In the past, though, we have tailored it to drivers. So for instance, in 2021, we had a Rocket League control scheme where a trigger would cause you to go forward or backward. And that's a lot of just what does the driver prefer and how are they most fluent. We have active braking enabled. And what that means is that if you aren't powering the drivetrain, will actively brake instead of coasting. It makes controlling around the field a lot more intuitive, especially in this game when you have to stop at a pole. One of the things that we do differently as opposed to other teams is that we switch between speeds of our drivetrain. So if you're in a certain speed based on the state of the robot, full power on the joystick, maybe 0.5 power on each of the motors. And that's really important because depending on what mode you're in, you're going to be going different speeds. You're going to have less control over the finer details. So what our driver would do is that while going to a pole, they would be max speed going to the pole and then slow down to a much slower speed when trying to adjust to actually hit the pole. Although later in the season, that became less important with pole stabilizer. When coming in to pick up a cone, you would start really fast and then gradually slow down through the different control speeds so that you would have a finer control when actually going to pick it up. One thing that we do differently from most teams is that we don't use a power curve. So the two blue lines are example power curves that some teams have used where you have like a sigmoid curve or an x cubed. We just use a linear control. This is partly compensated by the different control speeds. So we don't need as much control in the slower areas of the drivetrain because we have 4 different speeds that we can plug between. And a lot of that just comes down to driver preference, where it was most intuitive to not have that power curve.
So wait, what kind of drills did you do for driver practice?
There are a lot of drills we did. One that we found was pretty effective for MTI at least was that if you gave each robot, say, 11 cones, because on average you would have 10 placed in auto and then 10 would go to each robot if they're relatively equal. So if you give a robot 11 cones and you give a human 11 cones and then you just play out the match, who can score the most points and crucially, who can win that ownership battle. And it means that we can realize pretty easily that placing a lot of cones at the end of the game is really important. So what we ended up doing is we ended up placing, say, 5 in the first minute 30, and then placing the last 5 or 6 in that last 30 seconds in order to maximize the amount of ownership you get. We also did another drill where if you just toss every cone on the field and say, pick them all up, it can really help the muscle memory of picking up fallen over cones such that we could get pretty fast with it by the end of the season.
Another drill that we did really early on in the season in order to get our drivers used to driving, because we had one new driver on the team, was setting up just an obstacle course on the field through the junctions so that they were able to traverse as fast as they could between the poles and get a feel for how you actually move through the field.
So now I want to jump into our secondary control a little bit. So for starters, on our robot from a drive perspective, everything is a preset. So the drivers are never having to go into manually controlling anything about the secondary subsystems. And that makes it really fast, especially if we go back to our initial video of the scrimmage, which here I can actually go up to. We can see that everything is manual. So when the arm is being controlled, everything is being done with joysticks and nothing is very snippy or precise. This is something that we wanted to fix, and it's something you can see in the latter video that's really been changed because everything is being done automatically in a preset. So like that fallen over cone, that's a single button. The drivers don't have to move the arm up, then move the claw down. We also wanted to...
Oh, sorry.
Sorry?
No,
sorry.
Go ahead.
We also wanted to automate as much as possible. So by the end of the season, we don't have the secondary driver or operators, we called them, manually releasing the cones because the beam brake sensor on our pole brace would automatically release them. So here's a video of the robot going up, and then the pole brace line trigger is broken, and the claw immediately releases. And what that means is that we can approach a pole, release it, and immediately drop, and we can place a cone in 2 seconds from being down to it being placed and we're driving away. And that makes everything much faster and much more fluid if the drivers aren't constantly having to think about, okay, am I lined up? Can I release? And things like that. But one crucial thing we did is that we still have manual control. The drivers still have the ability to manually move the arm up, down, wrist up, down. And that makes you a lot more versatile when on the field if something goes wrong or if a situation appears that you just didn't think about.
So other than the pull brace sensor, do you use any other sensors to optimize your robot?
We use a couple different sensors. So one of the more obvious ones is encoders on each of the motors, especially on the arm motor. I'll get into that in the next slide, but we have a custom PID loop running on them so that it's really fast to control. Obviously, we have a camera on the front of the robot that allows it to read the April tag sensor. We experimented a lot with having a color sensor inside the claw, could detect when a cone was in the claw, and then it could automatically grab, so a driver didn't have to grab the cone either. But we actually found that it was slower because of the latency between the camera sees the cone and the claw grabs the cone. And so even as we tried to improve that by switching out the servo to make it faster, optimizing the code a little bit, we found that it was just faster for a driver to just hit a button.
Another one of those sensors that we have on the robot is on the very bottom underneath the carriage. We have 2 limit switches so that if the carriage is going down, it's not going to keep driving down into a place where it cannot go. Thus, we prevented overheating of the motors when they're stalling, trying to go down to a place where they can't.
Okay, so a couple other just cool control things that we do is we have a custom PID on the arm. Now, it's the reason that we chose to have a custom PID loop, or in our case, a PIDF loop, is because if you're using the default go build a motor go to position function, you're not actually running a pure PID loop. You're running one PID loop that that plots the position of the arm, so the plans a path for the arm to get to a position, and then another PID loop that actually follows that path. And for us, that's just really overcomplicated, and it led to the arm not going where it should go consistently, doing it slowly and with a lot of bounce back. So we have a custom PIDF loop that implements a feed forward coefficient, so a constant power that's always applied to the arm based on the cosine of the angle relative to the ground. And what that means is that we can constantly counteract the force of gravity with our PIDF loop, as opposed to the default motors, which just can't do that very well. We're using a standard Roadrunner with 3-wheel odometry, as you can see here on the base plate. There are alternatives. There's time-based, which you ran in 2021, 2022. But the problem with that is that it's really inaccurate, especially when going through fast autos. There's VSLAM, which I know a couple teams are using, but that we don't have a lot of experience with and haven't tried. And then there's also something which is a little more simpler, like a distance sensor, which we actually ended up putting on our 2022 robot. And that can tell you how far away you are from the walls. And so for certain games, that may be best. You don't have to worry about a complex odometry system, and you can just put a distance sensor on it. And that definitely improved how he performed, but I don't think it's going to get the accuracy that you're going to get with some odometry. I believe that's the end. No, okay. So I can talk about our vision system a little bit. We're basically just using Easy OpenCV. It's the library that first has now ported into the standard library for the 2024 season, or I guess 2023, 2024 season. And so it's pretty simple. It should be accessible to most teams now. We're using April tags, and those themselves have even gone through iterations. So we've played with the sizes here a bit, because initially in the season, we wouldn't be able to consistently detect the April tag due to the warping that the cone had tag image. Eventually, we ended up putting 3 medium-sized April tags on the sleeve, and that ended up being really consistent.
So during the autonomous period, how do you limit some of the issues that can happen, like during the game?
What kind of issues? Like hitting another robot, or like
like things like that, like.
So honestly, we don't do a lot of on the fly, are we hit by a robot? I know Wolfpack does a lot of that. We don't, because it's just kind of unnecessary for what we're doing. At some point, it's really hard to recover, and your auto is not going to be quite as good. So we run the auto no matter what. We have done a lot of things to limit interference by the field on the robot's auto. So we've played with paths a lot for how to avoid the signal cone, because when you ram into it, the way our robot's constructed is that the signal cone would often be carried with the robot as it would do the rest of the auto path, and that could block a pole or knock over the stack, which is really bad. So we did a couple of things like changing the path so it would rotate as it traveled to a position and kind of spin the cone off. Near the end of the season, we added literally just a safety glasses brim would kind of spin the cone off as a ramp. But we don't do a lot of on the fly changing to the autonomous like some teams may do. I believe that's the end of our programming slides. Yeah, I have a couple like tips for random odometry things. So we use open odometry pod design. One thing that we've seen some teams do is that they will modify their Roadrunner constants, so how the PID is tuned, what the constants are, while trying to tune autos. I think that's a mistake. I think that you want to compensate for the error, especially like at a competition while you're tuning a specific autonomous mode. One thing, the biggest flaw with Roadrunner when you're making paths is that most paths are not continuous. Unless you're doing 2 splines, Roadrunner will actually have to pause between commands. And that's one of the biggest reasons I think teams have started to create their own path following systems, is because splines make the robot really unversatile. And if you don't want to do splines, then you have a lot of pauses in your autonomous. We have also played with bi-single wheel motors, such that when I send 1 power to all the motors, they're not all powered with 1, because not all motors are created equal. 1 power on 1 motor may not be 1 power on 1 motor. They may still go different speeds. That's it. That's our program. If there are any questions, I'd love to answer them.
I actually have a question about mechanical. So can you walk us through like some of the most significant iterations on your robot that have like improved your performance on the field? I know
Yeah.
you've mentioned some of them, but were there any others?
Yeah, for sure. So Sean, if you'd be willing to move back to our right here, you have what I like to call our iterators graveyard. So on the left here, and then eventually what we set up on a presentation on the right is all of the different 3D printed pieces that we went through while we were trying to create that final robot. You can see a lot of what it is pieces of the claw, specifically the fingers that we were using. And you can see on the right, many of those are broken. So while we were testing, specifically while we were running autos, things would hit other things like they will on the field, and they would break, right? So every single time that happened, we had to figure out what caused that issue, and we fixed it. This is what we did for every single piece on the robot. We did that for the shoulder, making sure that the connection to the actual carbon fiber arms was as strong as possible, making sure that we were effectively locking onto the cone on our claw, and making sure that our rotation was as fast as possible. Another one of the things that we iterated on, it wasn't as major, but the side plates that we have on the side of our robot, the ones that say 11329, initially they were a lot shorter than they are now, I think about 1/4 of an inch. But we extended those downwards like we did with the Lexan plate on the bottom of our base plate in order to prevent us from getting stuck on top of the ground junctions. So here is another place where you can see some of those iterations. That second image there is what I was talking about earlier, with where we just had 2 plates on the very top of our robot with 2 servos on each. And you can see how that puts a lot of the weight very high, as well as using those metal gears as opposed to using a plastic chain and pulleys. Those are kind of the most significant iterations that we went through on the robot. I'll say that the claw itself went through, I think, about 6 or 7 before ending up what it is now. Some of those initial designs were a lot more flimsy and a lot less quick. You can also see in that third photo there, we had an iteration where it was a large custom molded silicone pad that would then connect onto the cone. But we found that was inefficient, difficult to make replicas of in case we needed to replace it. And we found that weather stripping just on the side of our claw pieces did the exact same thing and ended up being more effective.
I think that's all. Did you all prepare for like engineering notebook questions or not?
We have our engineering notebook up. Do you want to switch to that? All right, give me a second. Okay. All right, this is our engineering portfolio. It goes through most of the same things that we talked about in the initial presentation. But if you have any questions about it, I'd love to answer them.
So is there like a separate team to like work on the engineering notebook, or does everyone like contribute to it and work together to create it?
So for the most part, we have everyone works to create it. We definitely don't have a separate team that says you're responsible for the engineering notebook this year. And the reasoning behind that is just because it's not going to turn out quite as well. So for instance, we have a lot later in the engineering notebook about here's our design, here's why the design was done the way it was, and someone who didn't directly work on the design is not going to be able to articulate that as well as someone who actually made it. It's the same thing behind like programming. If someone doesn't program, they probably won't be able to articulate programming quite as well. And so for this reason, we generally make the robot, then its competition approaches, draft the initial, here's what our team is, here's what our outreach is in the engineering notebook, and then have the leads of each section come in and write their part.
And when does your team start working on the engineering notebook? Is it like gradual throughout the season or like all at once, like right before the competition?
So yeah, we definitely start off our notebook as early as we can. So we had a Google Docs that we just every day we would type up updates for what each of us were working on, just trying to document everything that we were doing, because it's not documented, it didn't happen. And by doing that, it's a lot quicker to be able to then move on to your actual engineering portfolio, make it look nice like we have been able to do this year, and make sure that everything that happened, the small things that you might forget that might actually be important later, are included in that engineering portfolio at the end of the day.
So what kind of like information is useful to keep in the engineering notebook? Is it like everything you've done in the season?
I mean,
most
pretty
important
much.
part
That Google
is
document is very, very long. I think by October or something, I had about 16 pages on the design of just notes from every single day of how I was working on it. And not all of that's going to end up being used, but some parts that you might not think are going to be used are. And that's what you're looking for. Those are those little pieces of gold that are going to help you out in your engineering portfolio.
So for the engineering portfolio, how does your team allocate or like organize each section in it?
Yeah, so I mean, if we just look through our engineering notebook real fast, and it's all public on our website if someone wants to go take a look, is that we start off with here's what our team is, here's how we function, here's our structure. We have a little bit on recruiting and some of our outreach, how we start doing things. We have a little bit on each people, how the team is valuable to them. This is some more outreach that we go out to, how we support other teams. We go into then our core design philosophy, how our strategy formed, and why we eventually chose the design we did. We start prototyping. So what were our prototypes? How did they evolve? Why were some of them bad? Whatever. We then kind of go into each subsystem. So what does it do? What are the constraints? Why does it do what it does? Here's the arm. There's, I think, a couple pages on the arm because it was, we had a lot to say. Kind of the process on the claw. Here's the two gear design that I was initially talking about. And then we jump into programming. So some of the cool programming things that we really want to point out. So in this case, we had odometry, how we tuned it, PIDF control as well as some of the presets and sensors, and then vision. Oh yeah, and then we have some scouting that we wanted to point out, and the electrical layout that we did some cool stuff on, like this voltage sensor or the lights on the side. And so in the main engineering portfolio, we put here's what our team is, here's how we do outreach, some subsystems, and the things that we really wanted to point out to judges that we thought were cool about our robot.
We really try and highlight the individuality of our robot, those unique things that are going to help us stand out from the rest of the crowd.
All right, I think that's it. And as we wrap it up, what are some of your goals for the upcoming season?
So as far as goals for the upcoming season, we have a lot of new people that we're hoping to develop. So we actually had like 30 new people show up at our call out meeting recently. And so what my main goal this season is we have like 5 people who are interested in programming. And so this year we had like 2 people who programmed the entire robot. And so being able to teach a lot of new people, here's what programming is, here's how you do it, such that they can program a competent robot by themselves is a big goal. Because if someone comes to robotics meeting and they don't learn something, they're going to drop it, they're not going to have fun. And so it's really important to us, especially the new season, that with all the new people, we don't say, sorry, we can't teach you, I'm going to program the robot, you can watch it kind of thing.
So we actually have 3 new members this year. What do you think is like the best way to like train them?
So I'm the lead programmer, so I can tell you how we've kind of taught programmers this year and in some ways in the past. And so what we started with is we started by just handing them on-bot Java and a drivetrain and saying, here's how you talk to a motor, here's how you can set power on that motor, make the drivetrain go. And then you can move into here's how this sensor is, here's how it works. And eventually you get up to the point where they can more or less program a robot by themselves. So whether that means last year's robot, they're giving them as a test or something else, that's been pretty important. And that's generally how we teach for each different subsystem. I'm sure Diana can talk a little about how she's been teaching design.
The philosophy that I use when I'm teaching is really I do, we do, you do. So first, I want to show you how I use this thing, how I'm able to create these designs. Then I'm going to work with you. We can make just some doohickey, so you can see how those things work personally, firsthand. And finally, you do it yourself, making sure that they have the skill and the competency and the confidence to do something on their own, something small at first, and then build them up to those higher level concepts, and then eventually full robot designs. So one of the things that we do over the summer, our kind of next line as lead designer has been working diligently over the summer to design a new robot base, something that we could use maybe in the future, and something that will train him up and make him ready and confident to start work on that robot next year.
And final question is kind of a fun one. If you could create one game for like any type of game for FTC, what would it be and why?
Personally, I'm a big fan of shooting games, especially when it comes to software you can do on-the-fly shooting. So I would probably do, if you take Velocity Vortex and you make the goals not spin, and then you triple the amount of balls field because only having 2 per team was really slow in my opinion, that is like my dream game because that gives you a lot of optimization when it comes to individual cycles. And especially when it comes to programming, you can do a lot of like tracking balls on the field. There's a lot when it comes to aiding drivers and picking those things up, as well as shooting at them on the fly. It gives teams a lot of leeway to how they're going to design the robot. How complex are they going to be? How simple are they going to be? Are they going to have a turret? Are they not? Are they going to try on the fly shooting? Are they going to have single intake? Are they going to have double? Do you want to do swerve since you might be fighting over balls? I think strategically it can be really interesting, and especially programmatically, there's a lot of opportunity for advancement.
For me, one of the ideas that I've had for a while after my first season, I working on it just as a kind of side project, is FTC Armageddon, which essentially that's the concept, which is essentially based on a post-apocalyptic world where we need to do tasks to make sure that you are able to survive, that your alliance is surviving. And I was really thinking of it as a lot more of a strategic game, not so much fast-paced, but more precision-based. So maybe we're doing tasks like flipping specific switches in a very precise order, and making it a little more dexterous than just purely speed and yeah.
And so, well, thank you so much for coming on our podcast today, and we'd love to keep in touch with you, and we can't wait to see what you accomplish next season.
Thank you so much.
Thank
Thank
you.
Thank you
you.
very much.
Thank you.
Bye.